Hey everyone, and welcome. Today we're going to look at graphing from a completely different angle. I mean, if you've spent your entire life thinking on an XY grid, get ready because we're about to break free. We are diving into the world of polar coordinates. Let's jump right in.
So for as long as we've been plotting points, we've pretty much stuck to the Cartesian system. You know the drill, right? Start at the middle, go right by x, then go up by y. And look, it's reliable, it works. But what if there's a more, intuitive way to do it? Instead of go right, then go up, what if we just said go this far in this direction? That right there is the whole idea behind polar coordinates, or as we'll call them, r and theta.
Okay, so let's make this official. Let's break down exactly what this new direction is all about.
And the definition is actually beautifully simple. You define any point with just two pieces of information. First, there's r. That stands for radius, which is just the straight line distance from the center, from the origin. And second, there's theta, or theta, which is the angle of that line, always measured counterclockwise from the positive x-axis. Distance and direction. That's literally it.
So you might be asking, why are we bothering with a whole new system? Well, it's because some things that are kind of clunky and complicated in that old XY world become just incredibly simple in polar form. I mean, think about trying to describe a perfect circle or a beautiful spiral. With polar coordinates, it's not just easier, it's elegant. And you're going to see just how elegant in a couple of minutes.
Now, if we want to work with both systems, we need a way to translate between them. You can think of what's coming up next as our Rosetta Stone, a way to convert between the language of x and y and the language of r and theta.
And here it is. This is the code. It's brilliant. Look on the left. If you have a polar point, your r and your theta, you can find its home on the xy grid using some basic trick. X is just r times the cosine of your angle, and y is r times the sine. Now look on the right. To go the other way, you use the good old Pythagorean theorem to find the distance r, and you use the inverse tangent for find the angle theta. This little table is your key to everything.
Okay, theory is great, but let's make this real. We're going to put these formulas to the test with a couple of examples right now.
All right, first up, a pretty straightforward conversion. We've got a point that's a distance of 4 units from the origin, sitting at a 60-degree angle. So the question is, where would that exact same point land on our old x, y grid? And it's really as simple as just plugging our values into those formulas. So for the x-coordinate, we take r times cosine of theta. That's 4 times the cosine of 60 degrees, which gives us a nice clean 2. For the y-coordinate, it's 4 times the sine of 60 degrees, which works out to about 3.46. And there you have it. The polar point, 4, 60 degrees, is the exact same location as the Cartesian point, 2, 3.46. Easy as that.
Okay, let's try going in the other direction now. This time we've got the Cartesian point, -3, 3. So that's 3 units to the left and 3 units up. What's our distance and direction? Now, be careful. This one has a little twist to it.
So we start by finding r. Using our formula, it's the square root of x squared plus y squared. That gives us the square root of 18, which simplifies down to 3 times the square root of 2. No problem. Then we find the angle theta using the inverse tangent of y over x, so 3 over -3. And the calculator tells us, -45 degrees.
Hold on a second. Does that feel right to you? Let's picture it. The point -3, 3 is in the second quadrant. You go left, then up. But an angle of -45 degrees is down in the fourth quadrant. So what's going on here? This is a super common trap.
So here's the deal, and this is absolutely crucial. Your calculator's inverse tangent function has a built-in limitation. It can only give you answers between -90 and +90 degrees. It can only see quadrants 1 and 4. Since our point is clearly in quadrant 2, we have to correct for this. And it's an easy fix. You just add 180 degrees to the calculator's answer to swing it around to the right spot, which gives us the correct angle of 135 degrees.
And now we have our real answer. The Cartesian point, -3, 3, is exactly the same as the polar point, 3 root 2, 135 degrees. So remember, always check which quadrant your point is supposed to be in.
Okay, so we've been converting points, that's cool. But the real power, the magic of polar coordinates, that comes when we start converting entire equations. So take this classic, x squared plus y squared equals 9. You probably recognize this, right? It's the equation for a circle, centered at the origin with a radius of 3. Now watch what happens when we convert it. Since we know from our little cheat sheet that r squared is the same thing as x squared plus y squared, that entire left side of the equation just becomes r squared. So r squared equals 9, which means r must equal 3. And that's it. The whole equation just says the distance from the origin is always 3. It's so direct, so clean. This is why we use polar coordinates.
And speaking of things to watch out for, let's take a quick second to go over the most common mistakes people make when they're first getting started with this whole system.
We've already hit the big one, the quadrant trap. Never, ever blindly trust your calculator's angle. Always visualize the point and add that 180 degrees if it's in quadrant 2 or 3. The second one is what I call the uniqueness trap. You see, in the Cartesian world, every point has exactly one address. But in the polar world, a single point can have infinite addresses. For example, a 60-degree angle is the same as a 420-degree angle, you just spun around one extra time. It's a really flexible system, but it's something you definitely need to be aware of.
So you might be thinking, okay, this is some neat math, but where would I ever actually see this in the real world? Well, let's look at one of the most direct and important applications out there.
Think about air traffic control. A radar system doesn't think in X and Y. It sends out a signal and it measures two things. How long did it take for that signal to bounce back, which gives it the distance, our r, and which direction did that signal come from, which gives it the angle, our theta. Radar literally thinks in polar coordinates. The XY map you see on the screen, that's just a translation it does for us humans.
And that really brings us to the big takeaway here today. Polar coordinates are so much more than just a different way to plot points. They are a completely different way of seeing the world. So the question I want to leave you with is this. What other complex problems, in math or science or even just in life, might suddenly become simple if we just learn to look at them from a new point of view?